In this video, I'm going to show you how to classify even and odd functions algebraically. So first of all, we want to prove that this function f of x equals 1 minus x squared is an even function. Remember, an even function is one that is symmetric about the y-axis. So one intuitive way to check that this is an even function is to sketch a graph of it. Here we've got a few function values in this table. When we plug in various values of x, this is what we get out for f. So let's go ahead and sketch these points and see if it is symmetric about the y-axis. So why don't we start with -3, -8. So go over 3 here, and then go down 1, 2, 3, 4, 5, 6, 7, 8. It's this point here. And then -2, -3. So go over -2, then down to -3. Then -1, 0. So over -1, and then y-coordinate of 0. Then 0, 1, right over here. 1, 0, over here. 2, -3, so over here, and 3, -8, so over here. And hey, that's looking pretty symmetric. If we connect up the dots here, we get a sketch that's like this for f of x. And yeah, indeed, that is looking symmetric across the y-axis. Cool. So we're getting the sense that f of x is an even function. But notice that the question asks us to prove that the function is an even function, not just be somewhat confident based on a few points that we've drawn here. We want a bulletproof argument that this function is an even function. And how do we know it's symmetric for all the points, not just the ones that we've drawn in here? The way to prove in all cases that the function is an even function is to think algebraically. So what does symmetric about the y-axis mean algebraically? It means that when we flip the sign of the input x, the output y equals f of x stays the same. We can see this in our table. For example, f of 1 is just 0, and 0 is also what f of -1 is. So when we flip the input from 1 to -1, the output is still 0. It's the same idea with f of 2. f of 2 is -3, and that's the same as f of -2. f of -2 is also -3. Same idea with f of 3. That's -8, and that's also equal to f of -3. So to prove that f is symmetric about the y-axis for any input x, all we have to do is prove that f of x is equal to f of -x for any input x. And we can do this by simply evaluating f of -x using this function definition here and making sure it comes out to the same expression as f of x. So let's do that here. So f of -x is equal to 1 minus, plug in -x for that x, so -x squared, which is 1 minus, well, -x squared, the negative cancels out and we just have x squared. And indeed, this expression matches up with the expression for f of x. This is really just equal to f of x. Great. So we've shown that f of -x is equal to f of x, and that proves with bulletproof total certainty that the function f is symmetric about the y-axis. So great, we're done. So now to restate the main idea that we've learned here, a function f is an even function if it satisfies the property f of -x equals f of x for all values of x. And that's just an algebraic way of saying that the graph is symmetric across the y-axis. So it's just a mirror reflection across the y-axis here. This side here is the same as reflected over to here. Okay, so why don't we go ahead and determine whether each function below is even. So the way we do that is to just check if it verifies this property, f of -x equals f of x. So for the first one, why don't we do that? Let's plug in f of -x, and the result for that, well, we just replace the x's with -x's. So -x squared plus -x to the fourth. And so let's simplify this a bit. Well, negative raised to an even power ends up canceling out because an even number of negatives means there's pairs of negatives and they all cancel out. So we've just got an x squared here. And it's the same idea with negative raised to the fourth power. All the negatives cancel out because there's an even number of them and they all pair up to cancel out. So it's just x squared plus x to the fourth. And that is exactly the definition of f. So f of negative x is equal to f of x. Great. So yes, this function here is even. So yes, even. Great. Let's try for this function now. So it's the same idea here. We're going to plug in negative x. So g of negative x, and let's see what that equals. So negative x squared plus negative x to the third. And again, the negative squared cancels out the negative, so we just have x squared. And then negative to the third power, well, two of those negatives cancel out, but then there's a third negative, so that stays. So just negative x to the third. And oh man, this doesn't look like it matches up with our definition of g. We've got our x squared, but it's minus x to the third. And if we try to factor out a negative sign, say we get like negative x squared plus x to the third, then the x to the third would match up, but then x squared is negative, and we also got a negative in front, so nope. So g of x is not even. Now let's talk about odd functions. So this is going to be a little bit similar to our discussion of even functions initially, but now we want to prove that this function f of x equals x times x minus 1 times x plus 1 is an odd function. Remember, an odd function means it's symmetric about the origin. In other words, its graph remains unchanged after rotation of 180 degrees about the origin. And again, to get an idea about whether this is an odd function, we can start by trying to graph it. So we've got some points here, some input x values and some output f values according to that function. Why don't we go ahead and plot them? So there's negative 3, negative 24, that's right over here. And negative 2, negative 6, that's right over here. And then negative 1, 0. Also 0, 0. Also 1, 0. A lot of zeros here. 2, 6. So that's right over here. And then 3, 24. So that's right about here. Okay, so now let's try to connect them up. So this is clearly coming up this way. And then what does it do here? Well, it's a third degree function, so it's only gonna have two kind of turns in it. Can't have more than 2 turns. So it'll go something like that. Okay, so there is our graph of f of x. And indeed, if we rotate it 180 degrees about the origin, so it goes from here to flip it around this way, then this portion here becomes that portion there, and that portion there becomes this portion here, and overall the function is unchanged. So we're getting a good idea that this is an odd function based on its graph. But again, this question asks us to prove that the function is an odd function. We want a bulletproof argument that this function is an odd function. And right now we're just plotting some points and saying, hey, well based on the graph, it looks like it's probably an odd function. But that's not good enough if we want to prove it. So to prove that this function is an odd function, we're going to do this algebraically, kind of like last time. So look at what happens when we plug in negative 3 for x. F of negative 3 is equal to negative 24. And 24 is just the output when we plug in 3 for x. So f of negative 3 is just equal to negative f of 3. And it's the same idea with negative 2 for x. F of negative 2 is equal to negative 6. And 6 is just the output when we plug in 2. So that's equal to negative f of 2. And you can also see f of negative 1 is equal to 0, which is the same as negative 0, so that's equal to negative f of 1. That case is a little bit less interesting, but it does still fit into the pattern that we're seeing. So to say that a function is symmetric about the origin is just to say that for any input x, we have f of negative x is equal to negative f of x. So if we can verify this property for all input values of x into this function, then it will be an odd function for all input values of x, and we can be sure that it's proven. Okay, so let's go ahead and input this negative x into the equation for f. So f of negative x is equal to negative x, just subbing in for that x right there, then times negative x minus 1, and then times negative x plus 1. Okay, so why don't we go ahead and factor out some negatives. So we'll factor out a negative from each of these terms. So we'll have equals negative 1 times x, and then times negative 1 times, factor out a negative from both of these, so x plus 1, and then times negative 1, factor out a negative from both of these, so x, and then minus 1. And now let's go ahead and let's group up our negative ones. So this is negative 1 to the third power, then times x, then times x plus 1, and then times x minus 1. And negative 1 to the third power, that is just equal to negative 1. And then we've got still x plus 1, x minus 1. And now let's think about rearranging this a bit to look like f. So it's got that x minus 1 in the middle. So let's put that there and change that negative 1 to just a negative sign. Negative x, we'll move that x minus 1 to the middle, and then x plus 1. And hey, that's the exact expression for f there. So this is just equal to negative f of x, and there we go. We've proven that f of negative x is equal to negative f of x for all values of x, and therefore we can be sure that this function is symmetric about the origin, which means it is an odd function. Alright, let's emphasize that point, that a function f is an odd function if it satisfies the property f of negative x equals negative f of x for all input values of x. And that's just an algebraic way of saying that the function is symmetric about the origin. It remains unchanged after rotating 180 degrees about the origin. So this section here rotates and becomes this section here, and the section that was originally with the negative x's rotates and becomes the section that's with the positive x's. You can also think of this as having rotational symmetry of order 2, because you rotate it 90 degrees 2 times. Or you can also think that you are reflecting through the y-axis and then reflecting through the x-axis, or vice versa, and it comes out to be the same. Either way you think about it, symmetric about the origin through rotations or reflections, the function is going to be the same if it's odd. So let's go ahead and determine whether each function below is odd. First, looking at this function f of x, let's see what we get when we plug in f of negative x. So f of negative x is equal to negative x to the third plus negative x to the fifth. And so let's simplify that. So negative raised to the third power is still just a negative. Negative raised to any odd power is still negative. So we've got negative x to the third. And then same idea here, negative raised to an odd power of 5, so still just negative x to the fifth. And we've got a negative on both of these terms, so let's factor out a negative. So negative x to the third plus x to the fifth. And hey, that's the exact expression of f, so that's just equal to negative f of x. And there we go. So f of negative x is equal to negative f of x. And therefore we can conclude that yes, the function is odd. Okay, so how about this function g? So let's go ahead and plug in g of negative x, and let's see what we get. So that's negative x to the third plus negative x to the fourth. Now let's go ahead and simplify that. So negative raised to the third power stays negative, so negative x to the third, and then negative raised to the fourth power, all those negatives cancel out in pairs, and then we've just got plus x to the fourth. And let's see if we can factor out a negative sign to make that match up with g. So if we factor out a negative sign, that's just x to the third and then minus x to the fourth. But this inside expression here is not the same as g, because this inside expression has a negative x to the fourth, but g has a positive x to the fourth. So we can conclude then that this function g is not odd. Now, one thing to be careful of is just because the function is not odd, that does not mean that the function is even. I know that's how it works with numbers. Like if a number, like 3 is not even, so therefore it's odd, and 4 is not odd, therefore it's even. But with functions, it's different. A function can be neither even or odd. So just because a function is not odd doesn't mean it's even. Or just because a function is not even doesn't mean it's odd. You have to check both cases individually. Great, so now we understand how functions can be categorized as even or odd or neither. And in the future, we'll learn about even more categories of functions, such as increasing, decreasing, and periodic functions.